Welcome to this presentation of the LITIC platform. My name is Schwarz and I want to show you two things today. First, LITIC is a tool to rapidly develop decision analytics applications in a graphical way, but also an example application from the world of finance that I took from this excellent textbook, Optimization Methods in Finance. We are going to use a simple MIP model to build an index fund. First, I want to thank the organizers for this opportunity to present at the summer school. It is very important for me personally. When I first participated as a student in 2009, I had already some exposure to combinatorial optimization from my university lectures, but here I could learn about the internals of MIP solvers and see the breadth of applications in this area, and this really convinced me to stay in this domain, and I haven't regret that choice 10 years later. I put here the URL of a website where you can download all of the data I'm using in this example so that you could run your own analysis, and I also reference the textbook again and give a summary of all of the logic that we encode here. So what you can see in the background is already a LITIC project opened, and it has some data in it which I will show briefly. So data in LITIC is either given as a dimension, which is a set of symbols. In this case I have some stock symbols, and then data is given in cubes that are defined over these dimensions. So for example, for each of these stock symbols I have a long name given as a text string. I also have the market capitalization, which is roughly the number of stocks issued times the price of them. And then I have closing prices. Those are given over two dimensions, so the date and the symbol, and for each date and symbol you have a closing price. And then you can already see the table view of LITIC, which you can customize easily. So for example, I can combine two columns here. I can also take this dimension and apply it to the columns, and now I have this two-way view of the closing prices. You can also just take a dimension and remove it, and this aggregates the data. By default it will just sum it, but you can change the aggregation method, and I can show the mean closing price. You can also sort data and do other things with it. For example, you could show a chart of the market capitalization and sort this one as well. Then you can see which stocks have the highest impact in this data, and you can even show charts inside of tables. So for example, if I put in here the closing price to this table, we see that the data is aggregated over the time, but if I drop the time here, I can say, oh, please use the time as a dimension for this chart, and now I have inline the time series visualized of the price. So this data ranges over the last 1.5 years, and it's daily prices. Okay, so let's talk about market indices. So we have data on individual stocks, but it's maybe overwhelming to look at. And so several companies define indices that describe a whole market as a single number. So for example, in Germany we have the DAX or DAX, which summarizes the 30 largest publicly traded stocks. And they do this by basically computing a weighted average of these, and the weight is given by the market capitalization. And we can also compute this index here by using derived data defined as formulas. So let me just create a new folder, and then we can create a so-called formula cube. So first I want to normalize the closing data so that it's easier to compare. So this is defined by symbol and the date, just as the other normal the closing price. And then each stock will get a weight inside of the index. So this is only per symbol, not per date. And then in the end we will define the index itself, which will have one value per date. Here I can show you our editor of the LITIC language. It's a graphical editor where you have some operators, and you can use, for example, the mouse and drag and drop to build expressions. So here I want to take the closing price, and I want to divide it by the mean. You can see I can also type in names and it will autocomplete. I can also here type in the name of a cube, and it will give me a selection. For all aggregation operators, you have a choice over which dimensions you want to keep. In this case, I want to keep the symbol, and which ones you want to aggregate over the date. So I want for each symbol the mean over the time window. And then for the weight, I use a similar formula. I use the market capitalization of each stock, but I normalize it by the total over all market capitalization. So both of these will give me numbers between 0 and 1, and then the index I will just use the product of these two. And then you can see it shows an error here because there is an extra dimension of symbol, because both of these are defined per symbol, and the result should be by date only. So this is basically a syntax error. And then if I drop the total operator on top, it will automatically resolve it. So it has already chosen the correct per and over configuration. Okay, so we can have a look at these in tables as well. And we can also compare now the original normalized stock prices. So we can make a chart over time where each symbol is drawn separately. So there's a lot of them. Maybe I can change the style a little bit to make it easier to see. And then I can, on top of that, create a new chart where I show just the index over time, and this one should be then more prominent. Okay, so we can see that the index shown in red is kind of like a weighted average of the movement of the prices of all of the individual stocks. Okay, and now we can talk about index funds. So this is an instrument used in passive investing, so where you don't try to actively pick what are good stocks to invest in, but you kind of concede that you probably won't beat the market on average, so let's just follow the market. And you just buy all stocks that are in the market according to how big of a component they are in the market. So this is very popular for people who don't want to follow market movements and want a robust return. But if you do it literally, it means that you would have to buy very small amounts of a large number of stocks. And this is awkward, and there are also a lot of transaction fees that you would have to pay. So the idea of an index fund is to approximate a market by a portfolio of stocks that just behave in a similar way as an index. And what this means for us is that we want to pick a portfolio of stocks that is a subset of these 30 here, of a small number that approximate the index that we just computed very well. And there is a model proposed in this textbook, optimization method in finance, that uses the idea of a clustering. So basically we cluster these stocks by a similarity measure into K groups, if we want to pick K stocks, and then in each of the groups we pick one representative, and then we buy only these representatives in amounts that correspond to the weight of the whole group. So first we need to define a similarity measure, and in this case we will use the correlation between the returns. So again, we will add some formula cubes, one for the returns. So this will be again per date and symbol. This will be daily returns, and then for the correlation of these, here I have to use symbol, and there's another dimension called other symbol. It's just an alias of the symbol dimension, so they have the same labels in it, but I want to refer to pairs of them, and so I use a different name. Again, I open the editor, and the return, for the return you basically look at the closing price from one day and the day before, and so we have a so-called reframe operator where you can look at a cube and say, oh, what is the value domain and what are the dimensions, and you can replace some dimension. Here I want to shift to the previous label of the date dimension by one amount. So in order to debug what we are doing in LITIC, you can always double click on any sub-expression, and then you get the data presented in a table. So let me put these together, and I can also look at this one. Okay, so it makes more sense to look at this way. Okay, so we can see that for one day, oh wait, this one didn't really work out. I showed the wrong one. So we can see that for January the 2nd, I have a closing price, but no previous closing price, because it would go out of the time window. But then for the next day, I have the number that you can see here, and then these ones correspond to the ratios between them, and I will from this subtract 1, and then this will give me the change in value. So here of this stock in the first from the first to the second day there's almost no change, but then from the second to the third day there's a 4% increase in value. And for the correlation we already have an operator built in. So here you can just drop in the return and then the return again, but we want to use pairs of symbol and other symbol. So here again we use the reframe operator and say, oh, instead of symbol you should refer to other symbol. And then you can look at these correlation values. And as you would expect, on the diagonal you have ones, and otherwise you have numbers between -1 and 1. We can also turn this into a little heat map by coloring the fields. Maybe I should use two different colors here. And we can also look at the histogram of values. And we can see that they are mostly positively correlated. Or in fact, in this case, they are all positively correlated. And sometimes very much so. Maybe this is not surprising because these are all large companies in Germany. Okay, so now that we have our similarity measure, we are ready to build our model. So for this, first I create some new data cubes. These will store the values of the decision variables in the optimization problem. So for example, I have one variable, a binary one, about whether or not a stock is picked in our index fund. And then I will have another decision that decides whether one stock is used to represent another one of the same cluster. So if this is 1 for one symbol and one other symbol, it means that other symbol is represented by a symbol and they are together in the same cluster. And then I will also take another scalar cube with no dimension and a real value for the objective. So we want to maximize the weighted similarity that we get. And finally, we also have one parameter, which is the number of stocks that we allow in our fund. Okay. And then we can create a new object, which is an optimization model. And it has, on the left side, you can see the same list of operators that we had in our formula editor. On the right hand, there are 3 sections, one for the solver output. So here we will just drop all of our decision variables. You can see it already detects the type of them, and you can add bounds and also domain filters, and then you can define the objective by specifying a single cube. In this case, we want to maximize the total similarity, and then we can use these operators to define linear equations and inequalities. So for example, we can define the meaning of the objective, can give a name. So the objective will be the weighted sum of the similarity that we get by representing some stocks with others. And here, so we will use the correlation between the symbols, but we will also use the weight of the stocks that are represented. So stocks that are have a high market capitalization, they will get a larger weight in this similarity. Here again, we have to refer to the other symbol. We want to use the weight of the stock that is represented. And then we have to make sure that every stock is only represented once. Again, we can take the sum over the represent variables, and it should be equal to 1. And here we sum over the symbols that can represent, but keep one constraint per symbol that is represented. And then we have another constraint that basically says a stock can only be used as a representative for a cluster if it's actually present. So if it was picked. So this looks, oh no, it's already done. Yeah, so every stock can only represent if it was picked. And then finally we want to limit the number of stocks that are in the portfolio. So here we can just take the sum over all stocks that are picked. So you can see that LITIC already deducted which constraints appear only once. So this one is just a single linear inequality, but this constraint is defined per each pair of symbol and other symbol, and this one is defined per each other symbol. Okay, so we should give a number here to make this concrete. So we allow 3 stocks, and then I think we are ready to solve, and it's done. And we can look at the solution. Okay, we can see that these 3 stocks are now part of our portfolio, and these are the stocks that they represent. So we can see, for example, this one represents itself, but also a large number of other stocks. In fact, we can here show the totals on the right hand side. So these 2 stocks represent 2 and 3 each, whereas the first one represents 25. So it must be really highly correlated with most of them. We can also pick here another number, solve again, and then this should be updated. Okay, so now we know which stocks we want to pick in our index fund, but we still don't know how much of each we should include, so the proportion they will take. And here we will just apply some simple post-processing. So we will create 2 new cubes. One of them will be for the weight of each picked stock, and then we can also compute the time series of the fund value over time, so that we can compare it to the original index. And then we can create a simple procedure. Here we can just drop in the model, and it will solve it in the first line. And then we can put 2 assignment statements. So this is just like a formula. For the fund weight, we use a weighted sum again. So we use the index weight times the represent solution. So if we go back quickly, we can see that in the model the decision variables are highlighted by using a bold font, and the other ones that are just data for the coefficients, I have the normal size font. Here we can see that the represent is again just a normal size font. So it's used as data here. It's no longer a variable, right? The result is now stored. Here again, I should use. Oh, sorry, it was a mistake. Out you go. I should use the other symbol. And then for the fund, we will use the normalized closed by the fund weight. Okay, and we can execute this procedure. And then we can look at, for example, this pie chart. And yeah, maybe let's add some more color to this. Yeah, and this gives us an easy way to just change a parameter and then solve the problem and look at the result. Okay, maybe we should also look at the objective value. So at best we can achieve a value of 1 here. And we can see that indeed if we limit the size of the stock, then the objective will become worse. If we use all stocks, then it will become perfect. For a more systematic way to compare solutions for different parameters, LITIC offers the Whatif analysis. So here you select a procedure to run, and then you can specify an input parameter. In this case it will be the number of stocks that are allowed in our fund, and then you can specify what kind of outcomes you are interested in, and when we run this it will solve the model for each of these values for a number of stocks, and then we can look at the outcome here. So for example here you can just see the parameter is created a new dimension, and then we can look at the objective as it improves for increasing number of stocks. We can also look at this in a scatter chart. Here and we can also look at the composition of the fund for an increasing number of stocks. So in the beginning there's only one, and then another one is added, but the first one is still dominant, and as more and more stocks are added, then each of them takes a smaller proportion of the fund. Okay, so that's all for this presentation, and I invite you to go again at this website where we have some additional material and the data for you to follow along, and also some suggestions of how you could extend this analysis.